Hi, Jeanette. Let me see if my sound is working okay, and I'm going to just start screen sharing. I'll wait for a couple more people, but throw up your questions, whatever questions you have right now, and then we'll go from there because this is your time for whatever you want to go over. I'm hoping I can. Oh, there we go. Now I can hear sound. So I'm just pointing out the things that we can go over. What other things screw people up and make them hurt their heads? We'll do
From the
arithmetic.
assignment 10, can we go over question, I think it was 4? There were
Which
like
one?
the two, you had to create two structs with student 1, student 2.
Okay,
That's
and
literally all
then
I
we
remember.
and that that's all you remember. That might be a bit limiting, but it's the you have two names or a bunch of things associated with them. You grab a pointer to one of them, you free the memory, and then see what crap happens.
There's like, for like one of the structs, there's like a static array, and then, oh, I don't even remember it.
Yep, I got that one. Okay, struct student one. If my solutions for assignment 10 are not up, I can post them now that it's due, right? So it's past due, so I can post them. I just needed to remember to do that. So if I don't do that soon, remind me because you should have access to it. All right, so here are my two different ways of doing things. I'm going to make a I think it was like a name, wasn't it? I think, and we'll make it like 200, whatever. And then we're going to have int ID, and then I'm going to have, I don't need anything else. I think that should do it. Oh, this was when I think there was another question where I make a dynamic array, I fill a bunch of points, and then I free the dynamic array, but I'm pointing to one of the pieces of memory. So that's a different beast than this thing, but this is the different names. I think this is what you wanted. Hope. And or we could have just a series of numbers. It doesn't really matter. The point is, this is going to be an array. This is going to be an array, or it is an array. The difference is what happens under the hood. So let's make a couple of these structs. So student one, very original name. Student student two. All right. So what happens when I do that? I'm going to make a data structure with all the variables in there. That data structure for the first one is 200 characters plus an ID. If I looked at it in memory, it would be 204 bytes in size, right? Because each character is 1 byte. We That's what the size of a character is. There's 200 of those in an array of 200, and then immediately after they like tacked on the bottom, you will see an integer. So there's 204 bytes in total. Hopefully that makes sense. The other one is a pointer and an ID. That's it. And Andrew, are you trying to talk, or the outline is around your head? That's all. So if I have a pointer and an ID, it is the size of a pointer. I think that's eight. Do believe that is 8 byte. 8 bytes. That's pretty big, but sure. Let's say it's 8 byte. 8 bytes, and the size of an integer, which is 4 bytes. So there should be a grand total of 12 bytes for the size of this thing. Now, it might say 16 in case it rounds up to the next power of 2, like to the power, like 16, 32, 64. I know that, so 12 is not a power of 2, so it might go up to the next chunk of power of 2. But other than that, it's effectively 12 bytes per name versus this thing is guaranteed to be 204 each and every time. Now, if your name is Bob, Well, 3 characters plus let's say their name later, the 0 at the end. Grand total of 4 characters, 4 bytes is what I need for the array. Technically, to store the full name Bob. Al's even better. That's 3 characters, right? A-L, and then the 0 at the end. So yeah, that's not 200 now, is it? So if I'm making a whole bunch of names and the names are really, really long, they're all about 200 characters, fine. But if I want to make sure I can support everyone's name, I need a big old name. I need a big old array. If it's static, I need a big old array each time. If it's not static, if I have dynamic array, I can say, David Sprague is this many characters long. I could say Jeanette Gonzalez is this many characters long. Danny Cole's even fewer characters, this many characters long. And they could be different sizes. They're just the number of characters I need for that person. I'm not wasting a lot of extra space. Otherwise, I need to make 200 characters, 200 characters, 200 characters, like they're big. But it does mean I need to call malloc a bunch of times for each of those things. So let's actually have a look at some of these things. So I can do st. So let's look at stu1. It has a name. It's an array, a character name, and it has an ID. So it will be of size 200. In fact, let's do our defines. Let's use our brand new tool that we have that we were just learning about, the define. It's a pre-compilation thing. This is if I just want to put the number 200 everywhere, but maybe I want to change it later. Max name len. And I'm going to use, it's going to look just like a constant, except for the difference is every time I see max name len, the compiler will actually swap out this word, plop in the hard-coded value 200. It's not a variable, no nothing. It is a hard-coded value. I'm getting shoved in there. Every single time you see max name length, it's the exact same as saying 200. If I do algebra, right, and I have x and I say, oh, well, x is equal to 4, I can swap out all the instances of x with the number 4 and just hot swap it. It's not the same as it being a variable. It's not the same as it being some kind of storing memory or anything like that. It is just literally just removing the word max name lang and shoving in the number 200 without you seeing it under the hood. So yeah, I'll leave it at that. I had a metaphor about hybrid cars, but maybe that's not that just popped in my mind, but that may not be helpful. So this thing is going to be, I know the maximum size of this thing. So let's play with this. So strcpy, so a string copy, doing the safe version of it. I'm going to put this in the name is the destination. I need the maximum length of that name could actually possibly be. Maybe I should make it +1. I need that extra 0 at the end. So I can move at most that's the number of characters. And this just ends up being one of those little fence post errors. People go like, is that working? +1. And let's say Bob Smith, because I just want some random generic name that's not anyone in particular. All right, let's have a look at what I'm doing wrong here. I need the string. Hopefully that'll do. That's not going to make any difference on an exam. It's more like, yeah, you just needed the functions that we're dealing with. You're not allowed to use the string class. That's C++. But if I need something that whatever's defining strcpy, good enough, right? I just want to I want to be able to convert. I'm going to take Bob Smith, dump that text into this name. It's still an array of 200 characters. Okay. And then I want to have like stu1 dot, let's get the ID 1, 2, 3, 4. Not very original. Okay. That's what I would do for the first type of student. But if I do, let's do the print f student with ID size. Let's do that. Okay. So what am I going to put in here? I'm going to put in stu1, stud, stu1 dot d, and then I'm going to put in the size of stu1. I want to see what that looks like. And then I'm going to do the same thing for the other student. I'm just going to copy and paste because I'm lazy. But before I do it, it's going to look exactly, it should look exactly the same when I'm done with this, except stu2, not stu1. I'm going to use stu2. I'm going to use stu2. I'm going to use stu2. Let's put the 2 in the name itself just to be on the safe side. 1, 2, right. But before I get going, I don't have an array. I don't get it for free like I do with the static array. The static array means when I start my program, I can predetermine how many bytes of memory I'm going to need. That's the point of a static array. It's going to make, while I'm compiling it, not when I run my program, when I compile it, it knows it will need exactly this many bytes of memory. That's how big the static array is. I know if I make this static array here, the static array in here will require 200 bytes plus the other 4 bytes for the integer. You will need from the system 204 bytes. The compiler, when it makes your program, says, by the way, I'm going to need exactly 204 bytes for this, and this number of bytes for that, and this number of bytes for this. It has no clue how many bytes you need for a dynamic array in advance. It says, I'll need a pointer. I need to store that somewhere. But I got no clue how big the program is going to, how much memory the program needs for the dynamic array. It's dynamic because when I run my program, it will then determine how big that array needs to be. That's the weird thing about dynamic arrays. It's done at runtime, not when I compile. So if I try and make a huge static array and it's too big, let's say I try to make a dynamic array of size, see if I can do this, -1. Let's remember that how 2's complement works. 2's complement means that when it goes beyond a certain point, it becomes negative. -1 is actually the largest number of ones that we have. It's just a whole slew of ones. Great question, Kenneth. So we'll get to that in a second. Remind me to make sure we get to that in a second. Those aren't the same things. So what I'm going to be doing here is, so if I have this is some massive number, right? If the number is too big and I cannot allocate that much memory, it can yell at me before I compile or when I'm compiling. It will not yell at me at run. I don't want it to yell at me at runtime. If I'm asking for too much, it will yell at me and say, whoa, 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 whoa. No, you can't have more than that many bytes of memory. That's just stupid. And just shut me down. I won't even be able to compile my program. Dynamic array is you ask for that many bytes of memory at runtime, and it has to figure out either to give you that memory or to say, no, I'm not giving you squat, and get returning null, as in I give you nothing. So it gives you, there's pros and cons to both, but a static array means I can't change squat. I can't make it variable size. I can't figure it out on the fly. If I have a program, when we do 2400, we'll be drawing different shapes on a GUI. So you use a mouse to draw a couple shapes. Depending, how many shapes do you want? I don't know how many shapes you want. You're doing it using a mouse to do it. Since I don't know in advance, I can't determine how big that array has to be. Maybe you want 200 shapes. Maybe you want 2. Dynamic array will let you do that. It'll allow you to add more shapes if you need to. Static, too bad. You're out of luck. If you want a static array to be bigger, you're completely out of luck. That's the problem with a static array. Okay. First off, for a dynamic array, I need to make my array. I need to ask for that memory. So stu2 dot a name is equal to, I'm going to ask for a certain number of bytes of memory. So I'm going to call malloc. Maybe I want strlen of Bob Smith. How long is Bob Smith as a string? Plus 1 for the space at the end, and we will get to Kenneth in a second. So that is how many characters I'm going to use, but I'm not done because I want to force you guys into this habit. Where is it now? strlen, okay. Times size of char. A character is 1 byte, but you do not want to rely on this. You want to force that case. So here's my string length plus 1. That's this thing here. I'm missing a parentheses right here. So let me make sure I'm not missing something else. Let's see. Size of char. This is just a parentheses issue. Size of char. This is the outside parentheses. And that's this char here. The string length.
Jeanette just said that your string length is missing the R.
Oh, that's the R. What? Say that again? Yeah. you caught it before I was able to catch it. Very nice. Nice eye. All right. String length. I do need a parentheses around that plus 1 because I want to do that math first. I want however long Bob Smith is. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 characters that I want. That's 9 characters long, plus I need that 0 at the end. Malloc is undefined. I'm going to just use. I'm just going to brute force ignorance this thing here, just for the demo. H. Or I could just see what this thing gives me as error message. Let me see what this thing gives me as an error message. Malloc, it's weird that they don't even allow it to be some default thing, which I find shocking. So I'm asking from the computer, can you give me 10, the caret length is 10 times 1, so 10 bytes of data. I'm going to pretend that 10 bytes of data is actually a whole bunch of characters. Each character is exactly 1 byte. It happens to be in this case. So I have 10 of these slots available to me. And now that's my array that I'm dealing with. And you'd say, why would I want to do this? Well, this thing up here is 200 bytes of data. This thing is 10. There's quite a difference between the two. Okay. And then we did the exact same thing as before with dynamic arrays versus static arrays. Nothing has changed there. I did the exact same thing for the ID. I did the exact same thing as printing this whole thing out. And I'll get to, Kenneth, I'll get to your question in 2 seconds. Let's see if this actually, I need to return 0. Let's see what other errors I have. Return 1 if I wanted. All right, did I change this thing? No, I didn't. Must be greater than 0 if we say, let's say 40,000. See if that, you have to need for that. Damn, it allows me to have 40,000 bytes or 40,000 characters or 40,000 bytes per struct. Put another 0 in there. I'm not sure if it's going to blow up on my face or not, but that is a ridiculous amount of that's just using Google Drive. That's not an error in my code. Hold on. Yeah, that's ridiculous that it allows me that many bytes in a static array. But all right, I'm using 200 plus 1. In the main and out the array with size 4,000. Oh yeah, I was just testing out the -1 thing. So isn't that because you use the max name length in the main and not the main array? The problem for that was max name length is 200. I could say it's only 200, but the array could be way bigger. This is why you use constants, because if I hard coded the value 200 here, but I have a different variable here, they happen to be both 200, and then I change this one up here, what happens? They're no longer in sync and things blow up in my face. It's bad. Define 200, not the 4,000 for the struct you put in. But I could make the struct way bigger than what I'm allowing this thing to be. That is what my point is. There's nothing, I could put 10 here and it will still work. It'll blow up as soon as I go over 10 characters. This is the sanity check. That's what the S is for. It's the sanity check. If you're transferring more than this number of characters, explode. Just yell at the user, essentially. That's what that underscore S in string copy is doing. All right, I have it running. Let's have a look at what we get here and see what we see. And then I'll go over this very, 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 very common problem with strings. Oh, I got some kind of weird error. Let's find out what we have. Exception thrown. Where's my exception thrown? Okay, size 8. I'm going to put a breakpoint in here. There's something I'm doing stupid, but let's find out. The name goes in there. 2. Student name. Print F might be a problem, but I don't know if it is. Size of stu 2. All right. So I have a couple. I have one more thing I also want to make sure I do. Free stu2.a name. When I ask for memory, I want to make sure I give it up. I free it up. If stu2.a name does not equal null, so I don't try and free it up twice. And you'd say, well, of course you didn't free it up twice. And I'd say, yeah, in this example, you probably definitely know that you didn't free it up twice. But half the time, your code gets really out of hand. And I want to get into the good habit of always checking to see if I freed it up first. And then if I didn't free it up, then free it up. Because if I did the same thing another time later, let's say I accidentally put a 1 in here. I want to make sure that I'm not having this happen all the time. So let's see this in action. Okay, let's see if I get my error message. Oh. This is just some. This is a weird error, by the way, in case you're wondering. Let's have a look at what this thing says. First of all, I want to return 1 just to be on the safe side. But this is blowing up right here. I'm calling malloc, stu2, string length +1, the size of the character. That's the size of my malloc. It should, thank you. That's what you're talking about, Jeanette? Nice eye. Let's actually do this in a different way. Let's do unsigned int text len. Let's do it this way. I don't want a text. With that, the dynamic array's length. Okay, that's my dynamic array's length. I want to use that same thing to make sure it's safe. I think you're right that it might be blowing up due to that, because it's trying to copy over up to 200 characters. It might go over the limit. So it shouldn't have caused an error, but I want to make sure. I'm making sure that I don't copy over more than this array will support. Array will support. I copy all those characters over. I set the ID, and then I want to do this. Okay. Might still cause a problem, but free up, name, return. Okay, something magic happened there that made it not blow up in my face. But let's have a look at this. What did I say the size of this thing was? I said it was going to be size 8. The size of, I guess, a pointer has to be size 4 bytes. Why? Because I know the size of an integer is 4 bytes. And the total size of this thing is 8 bytes. Right here. The other one is 208. So I have an array of size 200. 4 bytes for the integer. And then it must go to the next power of 2. I'd have to double check on that. 204, 208. I want to look into that thing. It might be rounding it up to a slightly higher value, but it's a big number versus this thing. This is 200 bytes more than this thing. And as a result, if I have something that's that much bigger, if I make an array of these student structures, it'll be that many 200 multiplied by however big that array is. It gets very big very, very quickly. Okay, on to the question of the hour. What is this thing here? It confused me to no end too. What is that? See, if I put that down as something, we'll see it in action. Let's see. Char my name. It should yell at me. Why is it yelling at me, huh? It happens, it knows it's size 10 because there's exactly 10 characters. There's 10 characters, well, 9 plus the 0 at the end. But it's also saying it has to be a constant char. It's a constant char because I cannot modify Bob Smith. So imagine hard coding a value. Let's pretend 1, 2, 3, 4. If I give you 1, 2, 3, imagine it's like 1, 2, 3, 4. 1, 2, 3, 4 is a number. If I say I'm going to change that number to 1, 2, 3, 3, you can't change a number. You can change a variable that's storing a number, but that constant value, you cannot redefine what 1, 2, 3 means in mathematics and make it something else. I'm not making a variable. It's not supposed to be changed. It is just characters I'm not allowed to modify. Does that make sense? So I make this array of characters that I'm not allowed to touch. It's read-only. Think of it that way. It's read-only information. If I give you a file that you guys can read, like a Google Doc that is read-only, you're not allowed to modify it. I might be allowed to modify it, but you're not allowed to modify it. The computer is doing a whole bunch of stuff behind the scenes, completely unaware to you. You don't know where this thing is located. You don't know how it works. You don't know anything. You just know there's this random array named Bob Smith. How come you use char star, not char my name is equal to Smith? So what ends up happening here? This is just some array. Now, if I want to copy stuff over, or I could have a pointer to Bob Smith. I could. I can't change it. I can't modify it. I can't move things around. If I want to do anything with Bob Smith other than just look at it and say, oh, what a pretty name, there's nothing I can do, right? If I want to make anytime I give you a function that says, rotate this character or change this character or encrypt this character, if it's one of those things, I'm not allowed to touch it. It's constant. It's like changing what the number 1, 2, 3, 4 means. You're not allowed to touch it. You're not allowed to look at it the wrong way. It's there. It is what it is. That's why I can't do that. So what you're saying is, why not use char my name is equal to Smith? Let's try it. So Bob Smith. Okay. So what happens here? This is saying I have a character pointer that I did not state is constant. So if I do constant character pointer, hey, it's happy. It is a character pointer and I'm not allowed to touch it. That's what that thing says. You try and change it, it slaps you in the face. I can't move things around. I can't reproduce things. I can't do squat with it. So I could have, my struct could have, let's make one of those structs. Struct 3, let's say. That there is actually going to be a problem with this. I'll just tell you that in advance. All right. Constant, at least it should be a problem. All right. So far so good, hopefully. And let's make one of these things. So print out that. Okay. Okay. 2, 3 dot a name is equal to Bob. Now I'm not sure it's actually going to work, if that's going to be okay or not. I thought it would actually blow up in my face, but maybe it won't. It doesn't seem to be blowing up in my face. That's good to know. Can I change it? No. So the name could be hard coded in there, but I'm not allowed to change it. I can't modify it. It's generally, unless you are definitely not going to change it no matter what the occasion is, I won't use this kind of thing unless I know for sure I am not changing it. I will not make a pointer to one of these things unless I know for sure I am not going to change it. That's the key of all this. Sorry, cat walked in the room. So that would be fine. But if I want to modify Bob Smith, or I wanted to add a middle name to Bob Smith, or I wanted to make it B Smith, or I want to do something else with it, I can't use this. The moment I have to make any edits to it whatsoever, nothing I can do. If it needs to be variable, I can't use this. Think of this like a constant. It is a constant, really. So if it's okay to have a constant, great. Have at it. Use it. Great. This actually will just be the size of this data structure right here will be the size of a pointer, a constant pointer, but it's a pointer. And not, I don't think it actually will be the entire array even. It might be. Let's have a look at that. And the size of the ID. Let's actually have a look at what this thing will give me, because I'm kind of curious for myself. If you're confused, if you don't know how something works, I always suggest just type it in, see what happens. Half the time you'll figure out what it's doing. All right, so same thing as before. Now I have a constant character pointer that I'm not allowed to modify. I want to see how big this thing is, if it stores locally or not. Okay. Oh, it's exact same size as what I had before. Why? Because this thing is stored somewhere. Where? I don't know. You know? No. You need to know? No. It's stored somewhere in the system. It has an address somewhere in memory, stored somewhere else. It's a special location wherever it stores all of its random hard-coded strings somewhere. I don't need to know that. I just need to know the pointer to where that location is. So I could do a bunch of these things, but I'm not allowed to modify that variable at all. It's just pointing to where this thing is stored in memory, and that can't be changed at all. And then I have another number. The reason why I don't want to just use, I don't want to just use char my name is equal to Smith. Well, it would have to, char is my name would be a single character. It can't be a string, first of all, right? Char star is a pointer to a character array. That would be fine. Char my name, a char is a single character. You can't have anything more. It's a single character. Char star is a pointer to, presumably, an array of characters. I am pointing to where the bunch of characters are located in space. That's what I'm stored there. A pointer to where a bunch of characters are located in space. Characters that I cannot touch, I cannot modify, I cannot look at the wrong way. Right? They are not for me to play with. They're read only. So, Kenneth, does that sort of answer your question? Nice. It's a lot of this stuff is until you play around with it, then you go, oh, that's what that crazy thing is. So because pointers and arrays and all this stuff all sort of works together, I'm pointing to this big chunk of memory somewhere where I get to carve it up myself. I take out if you want to think of it like, I take out a storage locker or one of those storage units for self-storage. I take out one of those storage units. I can put whatever I want in there. It's my storage unit. I can do with what I want. I'm asking for a big storage bin that I can put stuff into. I can carve it up, chop it up, whatever way I want. I'm asking for that memory from the system. But beyond that, you need to know where the thing is located, the address where this thing is located, and then I just walk in and start putting things in the storage unit. Oh, great. Let's go over resizing. So let's see if we can resize that string, because it's not exactly what we had before, but let's find out. So let's make a struct called update text, something like that. So we have a student 2, date student. Student. All right, that's going to be my function here. It is going to, oh, I need to put in another name. So I'm going to use a constant just for you guys. Constant char star new name. So the name is originally Bob Smith, and we're going to make it Robert Smith or something like that. Bob Smith, if you hadn't noticed, the length of this thing is exactly the size I need for Bob Smith. If I need to store Robert Smith, I'm in trouble. I've run out of space. Hopefully we're okay with that. So the moment I run out of space, I need to do something else. So let's figure out what we need to do here. I'm going to also, because I'm lazy, I'm going to copy all this stuff over. So, and maybe we should put an ID in there as well. Are these ID? All right, so we're going to pass in new data to this and the original data structure. We're going to change our values and return it. Okay. So what do I need? I'm going to make I could take the original student information and modify that and return it. Sure, let's do that. So that's not the hard part of this whole thing. And then I'm going to just return my original student information. So the student information, I can copy and duplicate that thing a million times. It just has a location where the text is, and it has the ID. So if I make changes to it and return it back, I have a brand new structure, but it's just pointing to the same chunk of memory where the words are. And this is where I need to have, instead of Bob Smith, let's use new name. So the length of my new name, this thing here, +1, that's how many characters I need to store things. This is the length of my new dynamic array. I then am going to call malloc on this, but I'm going to use something different here because I need to figure something out. So new name. It's the size of my dynamic array multiplied by the size of each character. That's the new array that I'm going to use. And then I'm going to copy everything over. So a new name, the array, the dynamic array length thing I'm going to be copying over. So it's not Bob Smith, it is origin. Bear with me for a second. So what is this going to do? This is going to make a brand new array, just like I did before, and copy. This should be exactly like I did before, but instead of putting it in the struct, I'm just putting it into a character array. And you're probably wondering, why the hell am I doing that? Well, because I still have the old character array to deal with. So I have this chunk of memory that I have. I need a bigger or different, at least, chunk of memory to store this name. So if I change the name from Bob Smith to Robert Smith, lead singer of The Cure, if you're anyone's Robert Smith for The Cure or Robert Plant? Oh God. Robert Plant's for The Cure. Robert Smith is who? Anyways. Or John Smith for economics. Anyways, there's a lot of Smiths. So if I have this name that suddenly needs to be bigger, I'm going to make a brand new array, set it up, and then change things around. So what I could do is copy all the old values to the new array, or copy the old values to this new array. Depends on how I want to do things. We can do the integer version of this after this. They're all going to be about the same, but this is just a different approach. I'm going to make a new array, copy all that text over, copy the new name into this new array that I'm going to be dealing with. But then I need to deal with the old array. I can't just get rid of it. If instead of this, if I just said original student dot name or whatever a student name was here, instead of making a brand new array with a brand new pointer, if I just stomped on or replace the old pointer, what happens? I'm pointing to this chunk of memory. I have this chunk of memory that's mine. And then I say, no, I don't like it. I'm going to go over there and go use that chunk of memory. I still own the old chunk of memory. I just walked to another place and just grabbed another chunk of memory from the system. In fact, maybe it's a bit too topical. Maybe it's a bit too, too recent. There's a big problem that they're having in Toronto right now, and probably all the way across Ontario, with vaccinations, because people are hunting around for the right vaccination, the vaccination that they want. If they want the Pfizer or the Moderna, they do not want AstraZeneca, they will actually subscribe themselves for multiple different places to get a vaccine multiple different times. They have those reservations. They're under their names. That's where they've reserved a spot for a vaccine. And then they go and get another vaccination place at another place and another and another and another. And then they find out which of those clinics gives AstraZeneca, and they just potentially just go to one of the places, get their vaccine, and just forget about the other ones. That means every single slot that they took, nobody else is getting. They had several thousand abandoned appointments for vaccines in the Greater Toronto area recently, because people were reserving multiple. It's human error, and they should have made the system better, but they're reserving multiple places. It's their place, and they're not giving back up their spot afterwards. So they find a place that they want to go to, and they just let the other ones hang, and who cares? But there's no consequence for them. For us, that's a memory leak. If I reserve multiple memory and just change where my pointer is going, I still own that old memory. I haven't given it back to the system. It's mine, and no one else in the system, no other program, no other application can use that chunk of memory. It's mine, and eventually your system runs out of memory. It's called a memory leak for that reason. You just sort of leak out a little bit of memory at a time until you run out, and then your computer hard crashes. Honest to God, if you have a game and you do this, and you're doing this every time you render a scene, if you have a memory leak every time you render a scene, you'll be losing a little bit of memory 60 times a second or 120 times a second, and quickly run out of memory and hard crash. Why we have to worry about this? Other languages don't have that problem. They've figured out that they have to do garbage collection, but garbage collection is slower. Okay, so what I want to do is I have this new memory. I want to eventually, I'm going to say original student dot a name is equal to a new name. Oh, that's why it's not a new name. Not the best variable names, but I'm going to change my pointer. But I don't want to just do that. The reason I don't want to just do that is that this is this. Okay, what's wrong with this one here? Oh, nothing wrong with it. The reason I don't want to just do this is because I still own the old memory. So I want to say if original student dot a name, if I have a memory already, I want to free it. I free the old memory that I have. Heck, I can even do this just to be really paranoid again. Set it to null to make sure everyone knows that equals. There you go. Set it to null to make sure everyone knows I've freed this thing up. But then I can send, once I've freed this, I've given it back to the system. Now I can ask for, I've already asked for the other memory, but now I can change what my pointer is pointing to. We could definitely ask another questions. That's resizing A10 afterwards from Jeanette. That's why we're doing that. Yep, we can definitely go over referencing and dereferencing. Let me check first. So, Jeanette, does that make sense for what we're doing with the resizing thing? With the integers, what we had to do is we had the original numbers. We needed to keep those. This one, I'm just throwing away the original name. If it goes from Bob Smith to Robert Smith, I throw out Bob Smith, all the characters for Bob Smith. We're put in brand new characters for Robert Smith. That's a different beast. But if I needed to keep Bob Smith and then add a couple characters like concatenation, I'd have to copy over all. I would just increase my array size, copy all of Bob Smith over, and then add some other characters afterwards. If that makes sense. All right. So, but this is, I get another array. I free up, I get another array. I free up the old array, replace where it's pointing to. And with numbers, if I'm trying to increase the size of my array, I make a brand new array, copy the old numbers over, change what I'm pointing to. Oh, free it, change what I'm pointing to. All right. Can we go over referencing and dereferencing because it confuses how they can store the value stored in an address, especially if you have a pointer to a pointer situation. Oh, Lord, pointers to pointers. Okay, so what do we have here? What if I want a, oh, actually, we actually have that. Let me see if I have a good example. Okay. Read top line. So it could be a file name or just file name. All right, I have a file name, like what we did before. It is a pointer to a file structure. That's what that thing is. We've seen that before as well. Okay, so what does a pointer to a file data structure mean? Well, the file data structure, I don't want to know how it actually works. I want to just be able to make one, use one, pass it around. So the file data structure, I'm never directly using. I'm just passing around the pointer to it. I don't want to actually know how it built together. I'm just passing the pointer. It's how I didn't make this up. Somebody else made this up when it comes to file IO. But it is being used. Because what they used to do is they'd have things like, let me see here, fopen, file name. This is the old way of doing file IO. And so I'd have it's making a file data structure, presumably dynamic, like a dynamic array, dynamic memory. making a file data structure that I'm passing the pointer to, and I catch the pointer in this, I catch the pointer to this data structure. It means I don't need to make an instance of file, because when I'm reading in this file, if I pass off the actual file itself, I'm making copies of copies of copies. It's weird. I make duplicates every time I return something. I take the original, the data, I pass values, not variables. So as a result, I need to pass a pointer so I have access to the original data structure. That's the reasoning behind this. But so that's the old way. Here's a new way. F open P file name. And you're probably wondering, why the hell would I do that? Oh, it's _s. Because it's more secure, it's safer. In fact, it's a safer thing to do. So what is this actually doing? This is saying, I have a pointer to a file's data structure. I need a pointer to that pointer because I want to actually change this value here. I want to directly change it. If I call a function, I will pass the value, not the variable. If I actually want to change this pointer, actually the pointer itself, I need to point to it, not actually pass the value inside of it. So I wish I had a good analogy here. Every time I call one of my functions, let's say, good function here. Let's do the ID here, a new ID. This will make a brand new variable. I will name it new ID, and it will be set to the value of whatever called it. It could be a hard-coded number, it could be another variable, whatever the case is, I get the value, not the variable. It's a brand new variable called new ID that is born right here and is destroyed right at the end of my function. That's how functions actually have been working the entire term, right? They get born at the very beginning, they die at the end of my function. If I want to make sure I pass the actual variable around or deal with the actual variable, the same variable, not duplicate versions of this makes a clone of the original value, if you will. Like it makes it the same value as whatever called it. So it's made here, it's destroyed here. If I want to have the original thing, I need to pass a pointer to a variable, because that's just, I'm going to copy the address. So I tell you what my address is, and then you copy that address, give it to somebody else, and you can copy that address, give it to somebody else, right? You can copy an address. I don't want to give you my house, right? That's a different thing. You don't want to have to duplicate my house each time, right? You're just passing it the where it's located. So one is I duplicate the entire data structure. The other one is I pass the address, the location for where it is, to the next one. And I can copy that all I want. It's just a location in space. It's just an address. So I can pass the address to another function. It copies that value, but it's still pointing to the same thing. This is, I'm at, what was my old address? 1019 Main Street. Okay, that's my old address. So I'm at 1019 Main Street. If I pass that address to you, you can say, okay, so the function passes in 1019 Main Street. This variable now has a value 1019 Main Street. It's the address of where where my house is. It's not the house, it's the address where it is. If you pass the address to the house, I can copy the value, not the variable, but the value. It still says 1019 Main Street. So when I have that address, I can go to the house and rob the professor. That's fun, right? I can go to the location if I have the address. So what a pointer does is it allows me to pass a pointer. If I pass in a pointer, it allows me to modify the original. I pass the address where that original is, and then the variable inside here can now change it to my heart's content. That's what this thing is doing. I have a brand new constant character pointer named new name that is pointing to the exact same chunk of memory as the last pointer did. They're both pointing to the same location. I didn't copy the data, I copied the location, the address. So they're both pointing to the same thing. What that's doing is it allowing me to, this thing now, I can modify the original, oh, maybe not this one, but I can modify the original value. This thing makes a brand new copy of a student2 data structure, copies what this thing here is, the value here, it copies what the value here is. But this is an address. So again, it's pointing to the same chunk of memory. It's making a brand new number, though, named ID, that has the exact same value as the original ID. Pointers to pointers allow me to do crazy things, like if I have a pointer, but if I have, let's say I have this pointer here, still got to be stored somewhere. There has to be a location where this thing is stored. It's a variable. I can store data in a variable. That variable is storing an address. So I can have an address to an address. So where are your contacts? They're in your phone. Where's your phone? It's in your pocket. So I point to my phone, which is the location where that's pointing to all my contacts, all the people that I know, all the people, how I can contact other people. It's pointer to a pointer. That's useful from time to time. Not always, but from time to time. Let's see if another example, if I can come up with one. So let's do pointer, pointer. See if I want to see if I can get a pointer to a pointer in a useful way. Because if I have, array of pointers, that will do. All right. Well, this might be not exactly what you're looking for, but let's see if we can do it. So I want to change student 2. I'm going to do this whole thing all over again, just slightly differently. I'm going to actually modify the original student 2 thing. So instead of just student 2, I'm going to take my original student, update student 2 as update student pointer. I'm going to take my original student. I'm taking a pointer to that data structure. And I'm going to directly modify it. But that means instead of everywhere I see original student, I'm going to change it around. It's going to be a pointer to a student, which a pointer to this student, and that student inside of it has a pointer, which is pointing to memory. Perfectly fine. It is a pointer to a name, which is another dynamic array. I have a pointer that goes to a pointer indirectly through a start. Pointer to a name, pointer to this. I can free my memory. I'm pointing to the original student. The original student then points to the dynamic array that I have, which then I'm freeing. Right? Because why not? Now I have actually modified my original student data structure. I'm not making a copy of it or anything like that. I'm actually just changing it. And let's make one more change. If I want to copy the actual contents, let's make it a void. Actually. All right. Update student pointer and update student should work exactly the same, despite the fact, in this case, I just passed in a pointer to the student, and the other one, I return a student. So let's go to my student data structure here. Let's change it right here. Actually, why not? And I'm going to update student with, so here's my thing. It's due 2. That's the actual data structure. I'm going to have the new name is Robert Smith. It's going to drive me nuts if I don't figure out who, Which Robert Smith? Keep on thinking The Cure, but I think it's Robert Plant. Maybe I'm wrong. No, it's Robert Smith of The Cure. Robert Plant is from. Oh, Robert Plant's from Led Zeppelin. That's what it is. Should know that. So here's Robert Smith. Now we're going to change the ID. We're going to change the name. Let's do one more than this, and we're going to update student. I'm going to copy it, uncopy it for a second, but I'm going to pass a pointer to student 2. I'm going to make it Robert Plant, just because I'm going to nerd out about this. And what would be a good number? 1984. Sure. Let's 89. The year Disintegrate came out. Okay. Good album. Creators of the South Park like the album too. Okay, so this is student BTR. All right, let's comment this out for right now. What we should see is Robert Smith with the 4, 5, 6, 7. Oh, it's not going to do that right now. We'll see why it doesn't do that in a second. Let's do it wrong, and then we'll see why and do it right in a second. Okay, must return a value. Oh, I'm just comment this out. So I'm going to use my new handy dandy little trick of using it to find. While something is false, it's never false, so therefore it's always removing the whole thing. Okay. Okay, this is going to be wrong. Just letting you know. It's going to be wrong because update student returns a student, and I haven't taught that returned student. It's just throwing back a student, and you're saying whatever, and just letting it go, essentially. Why is that? Get this again. I want to double check a couple things here. I got a weird bug. I'm going to remove what I did. Great. I'm going to put back what I did. This is a compilation thing, but that's a Google issue, not anything you would hit. All right. I'm going to run it again, see if I get the same error. Oh, that's weird. Oh, I know what happened. Oh, that's beautiful. What happened there? I forgot all about this one. This is even weirder. Can anyone guess what happened? What would cause me to get this weird crap? It's completely weird. The value is 1, 2, 3, 4, which I said it was. It is and it isn't. It's not that it can't find the value. It's pointing to Bob Smith, not the memory that I stored Bob Smith in. Remember I said, oh, we're going to make it Bob Smith, and then we're going to, and then we're going to change it. So what happened with Bob Smith? The array that stored the text Bob Smith. That's ultimately what then that's where the issue is. I still have an issue in here, but maybe it's what I'm being caused by here. What happened to the original name? Well, I freed it because I wasn't using it anymore. And then I'm going to return this thing afterwards. But since I'm not catching this return thing, I still have my original data. I just ignored, what this thing returned. I have my original data, but I have freed the memory where Bob Smith was. And that's why you get gobbledygook there, because the memory has been given back to the system and it's just gibberish there now. So what I need to do is be able to make sure I pass it back. So let's make sure I do it right. Okay, stu2 student. I want to double check this state student thing here. Pointer. Here's my original student. malloc, here's the size of my new name. By the way, if you want, assert new name does not equal null. It's a pointer. I want to make sure I don't have a null pointer exception. Okay, so just sanity check, make sure I don't have a null pointer exception. The size of my string is the same, it's right. The size of this thing is fine. I'm going to copy everything over. It is the new name is being copied over to this new array. And this is the size of the array. I've done a check for new name not being null. Oh, that is something I wanted to do. If I call malloc, I really should have something, some kind of sanity check. This is the warning. It's not preventing me from doing it. What I'm saying is if I'm making a new array, it could say, no, I'm not giving you any data. And if it does that, what do you do? Well, you just blow up and say, no, 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 something horrible happened. There we go. People are on the phone and kids. So let's do this. Robert Smith with ID 4567 has struct size 8. Gave back the memory. I gave, but because I made a brand new thing and I returned it, and I caught that new value, I called update student, threw out this student2 data structure, plotted on the other end, everything worked fine. But before, when I didn't catch it, I'm still pointing at the old and replaced my student data structure. I'm pointing at the old array that I gave back. That's what I got gobbledygook for. Okay, let's do it a different way. We know that one works. Let's see if this one works. This one I don't need to catch at the end. I'm passing a pointer to my student data structure, and I'm directly modifying, instead of passing in the copy of the values from the student2 and then replacing student2 with whatever this thing spits out, the values for whatever this thing spits out. Instead, I'm going to directly modify it. So it's a pointer to the student data structure, which has a pointer to a dynamic array of memory, which could have a pointer to this, which could have a pointer to that. I'm allowed to do all sorts of crazy things. I could pass in one of the examples you could have is I pass in an array of pointers. That is, those are pointers to pointers. That's allowed. Why not? I have an array, so I point to the front of the array. That array is full of pointers. Those pointers are useful for other stuff. An array of pointers, so pointers to pointers, a pointer to a pointer is what you get. Let's do that afterwards. So this should say Robert Plant when I'm done in 1989. That's just a Taylor Swift album. Robert Plant with ID 1989 has struct size 8. Oh, sorry, you can't see that. Boom. Robert Plant with ID 1989 has struct size 8. When I got rid of it, before I put that line in, it said Robert Smith with ID 4567 with size 8. That's why, like, there are two different approaches. One of them is I pass the pointer to the data structure, and I can directly modify the data structure now. The other one is I pass the data structure in, I get a copy of that data structure. I don't get the original, I get the values. And then I return the data structure where I get the values of the returned data structure. And then I put those in my original data structure. It's really hard to get through your head. It's really convoluted, but there's no easy way around that. Honestly, there's no easy way around that. Let's make a 2D array. All right. Okay. Here's what I'm going to do. I'm going to make a whole bunch of calls to malloc for each row of an array. So I'm going to make, so the width is going to be how big each one of these calls, one of these dynamic arrays is going to be. And then I'm going to make an array of pointers to the arrays. So it's an array or pointer to pointers. This would be the pointer to pointer thing that Kenneth was looking for. I'm hoping. You don't need the dereference, reference, and all that kind of stuff, although we can look at that too. So, so I want to do this in, I'll do something like this. Or my nums, let's say nums, very original name, is equal to int star star. It is a pointer to pointers. So I can put star star. It's pointer to pointers. It's the size of each element is a pointer multiplied by height. This is how many rows I have. And each row is represented by an array. So it's an array of arrays. Okay, now I need to make all the individual arrays. I is equal to width, it's going to be the height. So I'm going to make each row, and I'm going to call int each row. Okay, and then I go a nums at position I for each row is equal to a row. It is a pointer to pointers. So this is a pointer. This stores a whole array of pointers. So for each row, there's a pointer to the next array. It's an array of lookups to other arrays. Okay, and do I want to do something else? This will all be gobbledygook inside of it. I should have some kind of loop that fills in the values to some standard value. Okay, and how would I clear this thing? So how would I access all the individual elements? So how would I access the individual elements here? So let's do this. I could say it's the individual element at position 2. That is going to be row number 2, 0, 1, 2. Item number 3. Or column 3. That's what that would do. I could do something like this. And again, this is just play around with it. Plus 2. Dereference it. And then plus 3. Dereference that. Is in case you didn't know what I'm doing. Hopefully you'll see what I'm doing here. Okay. Also make an assertion here. Assert width is greater than 2. Assert it's greater than 3. See, let's say both are greater than 3, just to be on the safe side. Why not? What the heck is it? What am I doing here? What that makes no this is making no sense. The key is there's sort of an implied series of parentheses. What I have here is this thing here. What is this? This is saying go to row 2. When I go to row 2, I will get a pointer. So I could have also written this as set position 2. That is a pointer. The specific value, if I go, so this gives me row 2, and if I go to column 3, I get a specific value. Specific value here is equal to 4, or it should be. I want to double check this thing here. All right, it should be equal to 4. This is a pointer to a pointer. This is me having a pointer to a pointer that I move over 2 spaces in my array of pointers and get what the value is, which is a pointer to integers. And then I get, when that pointer to integers, I move over 3 spaces in that pointer to integers because it's an array, and I find position 3, and that's going to be equal to exactly the same thing as this. And yes, it is confusing. In fact, my number 1 rule is don't do this. It's a pain. I do it for an assignment to make sure that you've seen it. But if you're programming for real, you don't even maybe even do this. I will often do this. I know I have an array of rows of data. Keep it simple, get a row, then get the individual element on the row. Don't try and get all cutesy with like, oh, it's a row of a row of like, don't nerd out on this thing. Keep it simple so you can understand your own code later. This is an unruly mess. This is what I would be doing for pointer arithmetic to do exactly what this is. This thing right here, and exactly what this thing here is. And I want to see this in action because I want to confirm that specific value is equal to this value here, and that the whole thing is going to spit out the value, this value here. And then at the end of all of this, I actually want to return that. So return AA nums. When I'm done with making this array, I need to clear it up. I need to free up the memory. So let's do that. I'm just going to go to my main method. I'll call it new nums because just to show that they're not, don't have to be the same name. Make the ints 5 and 6, let's say. It's a 5 by 6 grid of numbers. And what I want to do afterwards is I want to free this stuff up. All right. How am I going to free up this array? Well, I can't just say, if I just said free AA new nums, what the heck happens there? Let me float this by you guys. You don't necessarily have to respond yet, but think about what the heck is this going to do? It's going to free my array that has a bunch of pointers in it. Is it going to free the other arrays, the arrays that are inside? No, it doesn't know. It just says it's a bunch of pointers. It doesn't know it has an array in there. It's just going to free a bunch of memory. It's not going to free up the arrays that are inside the array. It's just going to free up the outside array. So what I need to do is I need to free up each of these arrays. I just happen to know it is the number of rows is the height is 5, right? So I happen to know the height is 5. I should have some kind of value to store it, but free AA I want to go to each individual row, free the row. Set them all of each row to null, free the whole the outside array afterwards. It's big, it's convoluted, it's a pain in the bum, but it's what you need to do. If I have an array of names, I have an array of arrays. So it's a pointer to pointers. Each pointer inside, so in the array, it has a pointer to a character array, a pointer to a character array, because each one of those pointers is a full name. So name, 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 name. In order to free up all this, I free up each of the character arrays, then I free up the array that's holding it all together. And I have to do in that order, otherwise bad stuff's going to happen. So let's just compile it. Hopefully everything's going to work out fine for us. Run it. Okay, here I'm at my code right now. So I can't even look into my array very well, which is unfortunate. But let's see what specific value is. It should be equal to 4. That's what I'm expecting it to be. Specific value is equal to 4. All right. I always get nervous with this sort of thing. I never know. I work under the assumption that this is an array. This is row 2, column 3. You know, things can be wrong before for me in the past, so I want to double check. This is, I got row 2, column 3. There's no ambiguity on this one at all. There's no order of operations or anything weird like that. And then afterwards, I'm going to do a printf statement, and it should also spit out 4. So let's find out if this thing spits out 4. 4. The rest of the things are not initialized at all. I've only set one number in that entire 2D array. All right. And then if I continue, everything worked. Nothing blew up in my face. Me freeing up this array was I went through each row, freed each of the rows, and then afterwards freed the array that was holding all the rows. And the reason why I'm so lackadaisical about the difference between pointers and arrays and all this, because they're the same thing. The difference is if I have an array, I have to call free at the end, but all I know is I have a pointer to something. It could be a single number. It could be a full array. It's to the compiler, it's the exact same damn thing. It's some location in space. You don't know how big that thing is. You don't know what's stored in it. You don't know anything about it. You just know there's a position in space over there. And you as a programmer need to know how big if there's an array, how big that array is. You as a programmer need to know how things are formed, because all it says is you got an array with a bunch of stuff in it, and I don't know what you're using it for. You can do whatever you want in it. It's a storage unit that you can do whatever you want to. That's why we have to worry about pointers to pointers. This is actually a pointer to a bunch of pointers, because it's an array, a pointer, 2 pointers. The num, if I did, let's do one more, and then I'll let you go. Nums, and I did this, and then I'm going to make that equal to 17. What is that? That is the very first row. So row 0, column 0. It's the pointer to the first. It's a pointer to the first row, and then I said, and the thing that I'm pointing to is the very, very first element of the first row. So that is 0, 0. That's this thing here. At position 0, 0, the value is now 17. It's pointers to pointer. You have to play with it for a little while to really get your head around it, because it's going to make it's a little trippy. All right. Does that answer? We covered a lot of material here, so I'm hoping that made some sense. Some sense. Okay. You have to play with it, unfortunately. Yeah, even after 20 years, I'm still digesting some of the logic in this case. It's C is such an old language that it's the sort of philosophy is a sort of do-it-yourself philosophy where you do everything yourself. You don't, I'm made fun of by my in-laws because I'm not a handy guy, right? They're like, oh yeah, I put up my own garage today. Oh yeah, I fixed my own car. I'm like, I can work computer, sort of, maybe, right? This do-it-yourself attitude is what C is based off of. That you get memory, you choose what to do with the memory. You can do all sorts of crazy things if you want. It's just giving you memory and you figure out what you want to do with it. And as a result, it does take some time to get it around through your head. All right. All right. Thank you very much, everyone. Danny had to run, and I have to run too and grab some lunch. Hopefully that was somewhat useful, and I'll post the video as soon as I can.